Hello friends, my name is Madhusudan B. Miniyar. I am from Walchand College of Engineering and today I am going to explain the topic fragmentation. It is the introduction of the fragmentation, that is, some protocol can carry big packets whereas other protocol can only carry the little packets. For example, Ethernet packets can carry no more than 1500 bytes of data, whereas packets for mini wide area links can carry no more than 576 bytes of data, that is 576. The maximum amount of data that a linked layer packet can carry is called as MTU. MTU stands for Maximum Transfer Unit. Because of each IP datagram is encapsulated within the link layer packet of transport from one router to the next router, the MTU of the link layer protocol places a hard limit on the length of an IP datagram. Having a hard limit on the size of an IP datagram is not much of a problem. What is a problem is that each of the link along the route between the sender and destination can use different link layer protocols, and each of these protocols can have the different MTUs. To understand the problem better, imagine that you are a router that interconnects several links and each running different link layer protocol within the different MTUs. Suppose you receive an IP datagram from one link, you check your routing table to determine the outgoing link. This outgoing link has an MTU that is smaller than the length of an IP datagram. Time to panic. How are you going to squeeze this oversized IP packet into the payload field of the link layer packet? The solution of this problem is to fragment the data in the IP datagram among two or more smaller IP datagrams and then send these smaller datagrams over the outgoing link. Each of these smaller datagrams is referred to as a fragment. Fragments need to be reassembled before they reach to the transport layer at the destination. Indeed, both TCP and UDP are expecting to receive from the network layer complete, unfragmented segments. The designers of IPv4 felt that reassembling, that is, and possibly refragmenting datagrams in the router would introduce significant complication into the protocol and put a damper on router performance. Consider, if you are a router, would you want to reassembling the fragments on the top everything else you have to do? Sticking to the end-to-end principle for the internet, the designer of IPv4 decided to put the job of datagram reassembly in the end systems rather than in the network interior. When the destination host receives a series of datagrams from the same source, it needs to determine if any of these datagrams are fragments of some original bigger datagram. If it is determined that some datagrams are fragment, it must further determine when it has received the last fragment and how the fragments it has received should be pieced back together to form the original datagram. To allow the destination host to perform this reassembly task, the designer of IP, that is of version 4, put identification, flag, and fragmentation fields in the IP datagram. When a datagram is created, the sending host stamps the datagram with an identification number as well as the source and destination address. The sending host increments the identification number for each datagram it sends. When a router needs to fragment a datagram, each resulting datagram, that is a fragment, is stamped with the source address, destination address, and identification number of the original datagram. When the destination receives a series of datagrams from the same sending host, it can examine the identification numbers of the datagrams to determine which of the datagram are actually fragments of the same bigger datagram. Because IP is an unreliable service, one or more of the fragments may never arrive at the destination. For this reason, in order for the destination host to be absolutely sure it has received the last fragment of the original datagram, the last fragment has a flag bit sent to the 0, whereas all other fragments has this flag bit set to the 1. Also, in order for the destination host to determine if the fragment is missing and also to be able to reassemble the fragments in the proper order, the offset field is used to specify where the fragment fits within the original IP datagram. This bit is set to the 1 in all except the last fragment. Consider an example A datagram is a 4000 byte arrives to the router, and this datagram must be forwarded to the link IMTU of 1500 bytes. This implies that the 3980 data bytes in the original datagram must be allocated to 3 separate fragments, each of which are also have the IP datagrams. Suppose that the original datagram is stamped with the identification number of 777. Then the characteristics of these 3 fragments are as follows. Consider this figure. In this, the 4000 byte datagram, whose segment size is 3980 bytes, is sent to the router. Each has the maximum empty unit of the 1500 bytes, so the maximum 3 datagrams are passed through the router. For the first fragment, 1480 bytes in the data field of the IP datagram. Its identification flag is 777 and offset is 0. As offset is 0, it means that data should be inserted beginning at the byte of the 0. And as flag is a 1, it means that there is more data to be transmitted. Then, after first fragment, the next fragment is transmitted, who have also the data 1418 byte information. Its identification flag is also 7700. Offset is for 1480, meaning that the data should be inserted at the beginning. 1418 byte data should be inserted at the beginning of the second fragment. And flag 1, it indicates that there is more data to be transmitted. Third fragment. The third fragment of its size, that is 1020 byte, as already 14,080 byte passed 2 times information, remaining 1020 byte must to be sent, and its identification flag is of 777 byte. Its offset is 2960 byte, that is, it means that the data should be inserted at the beginning at the byte of 2960, and flag is equal to 0. It means that it is the last fragment. The payload of the datagram is only passed to the transport layer once the IP layer has successfully reconstructed the original IP datagram. If one or more of the fragments does not arrive to the destination, the datagram is lost and not passed to the transport layer. But as we learned in the previous chapter, if TCP is being used at the transport layer, then the TCP will recover from this loss by having the source retransmit the data in the original datagram. Fragmentation and the reassembly puts additional burden on the internet routers, that is the additional effort to create the fragments out of a datagram, and on the destination hosts the additional effort to reassemble the fragments. For this reason, it is desirable to keep fragmentation to the minimum. This is often done by limiting the TCP and the UDP segments to the relatively small size, so that the fragmentation of the corresponding datagrams is unlikely, because all the data link protocols supported by IP are supposed to have the MTUs of at least 576 bytes. Fragmentation can be entirely eliminated using the MSS of 536 bytes, whose 20 bytes of TCP segment header and the 20 bytes of the IP datagram header. This is why the TCP segment for bulk data transfer are 512 to the 536 bytes long. You may have noticed while suffering from the web that 500 or so bytes data often arrives at the time. In short, the fragmentation is processed by passing the maximum payload of the data by dividing into the small fragments with the help of IP header. Thank you.